Okay.
Thank you.
No problem.
Now I think we can start.
Okay, so let's start. We continue our sessions on SBMF, and it's my pleasure to introduce you the next speaker, Neda Saeedloei. Neda is an assistant professor of computer science at Towson University in the US. Before joining Towson University, she was an assistant professor in the Department of Computer Science at Southern Illinois University, Carbondale for 2 years, and University of Minnesota Duluth for 3 years. Before joining UND in 2014, she worked as a postdoctoral researcher at INRIA Roquencourt and then at the Naval Research Laboratory. Her research is focused on formal methods for system design and synthesis, specification, and verification of cyber-physical systems, including real-time systems and hybrid systems. She's also interested in models of computation and logic. Neda, thank you for helping us with the event. You can start.
Thank you for the introduction. Okay, so it's going to be a very brief introduction to timed automata. So let's see. Okay. So automata theory provides foundations for model checking. That is a classical, we are talking about classical models of computations, the simplest form, which were finite state machines that could be also extended with the stack in order to provide more support for more languages to be accepted. But the idea is that we always had automata or state machines to model the components of the system we wanted to model. And then the verification problem reduced to inclusion, whether the system specification is contained in the specification itself, means if the implementation of the system is included in the specification. When it comes to modeling real-time systems, finite state machines are not enough. So we need to extend our classical finite state machines with some capabilities in order to be able to reason about timing constraints. And this is the subject of this talk today. So let us start with a simple example. Let us consider a simple light control where we have a high-level model of a switching system where the light is initially off, and when we press it once, it becomes light. And if we press it once more, we want it to become bright if we press it quickly. And then if we do not press it quickly after it becomes light, we want it, and we press it once more, we want it to become off. But the question is, how are we going to specify quickly? So once more, when we press the switch once, we want it to be light. And if we press it quickly after that, we want it to become bright. Otherwise, if it takes some more time after the next press, we want it to be off. The challenge is how to specify quickly. And as you see, finite state machines would not enable us to be able to specify such a thing. And the solution for this is adding real valued variables, which are called clocks. So the idea is that along with the transitions, we are going to reset some clocks, which are real valued variables, in order to remember the time of various actions. And the clocks are going to progress at the same rate of the wall clock. And then later on, we can read the value of the clocks in order to check whether enough time has elapsed for various actions to take place. For example, here, when the first press is issued, we reset the clock X. So let me enable my laser pointer. Here is my, are you able to see my laser pointer? Okay, so here yes. I have clock X. With the first transition, clock X is reset to 0, so it starts ticking at the same rate as the wall clock. Now, the automaton switches to mode light, and now if I issue press once more, within 3 units of the time that the clock was reset, which means the time of the first press, then the switch becomes bright. Otherwise, if more than 3 units of time has elapsed, then the light becomes off. So that was an example of a timed automaton. In general, timed automata are extensions of finite state machines with real valued variables, which are called clocks. Let us look at the components of timed automata in more details. So we have locations, just like in finite state machines. P and Q are my locations. And then A is my action, which is same thing that we have in finite state machines, but we have two more components here. So Y less than 4 is a guard. So X and Y are my clocks. And then Y less than 4 is a guard, which is a constraint, which says this transition can take place when the input is A, and moreover, the current value of clock Y is less than 4. While this transition is taking place, the clock X is going to be reset to 0. And then the mode changes to Q, or the location now becomes Q. So while in Q, every time that C occurs, then the transition takes place and the clock Y is reset. And then finally, when B arrives, then if the value of clock X is exactly 5, the transition takes place and the location becomes 5. So we also have some invariants. Originally, invariants were not part of the classical definition of timed automata, but later on, people added invariants also to timed automata in order to enforce progress. Because without invariants, there is nothing that actually forced this automata to take the transition. For example, the transition from P to Q is enabled whenever the value of, actually in this particular example, it wouldn't make sense, but let us change this guard Y less than 4 to Y greater than 4. Then there is nothing that would force this automaton to actually take that transition while the value of clock Y is greater than 4. So in order to ensure progress, invariants are added to the locations. So here on location P, I have Y less than or equal to 5, which means that the automaton cannot stay here on this location P more than 5 units of time since Y was reset, which means it can stay in location P as long as the invariant is satisfied. It cannot stay there while the invariant is violated. That ensures progress. Okay, so now formally, a timed automaton is a finite set, it includes a finite set of locations, a subset of initial locations, a finite set of labels, and a finite set of clocks. And then we have invariants, which are essentially some clock constraints that are added to the locations. And then we have edges. So edge, each transition or edge of the automaton is going to take the initial location, the target location. A is the label, G is the guard, which is a clock constraint, and lambda is the set of clocks that are going to be reset along with this transition. Next, we would like to define the semantics of timed automata, but before that, we have to talk about clock valuation. So clock valuation is a function that at any point gives us the current value of a clock. So it is a function from a set C of clocks to all positive real values. So if V is a clock valuation, then we can define V plus D, which is defined V plus D of X is the previous, essentially D is some real value. We want to know if D units of time has elapsed, how the valuation is updated. So V plus D of X is the previous V of X, which is the previous value of clock X plus whatever time has elapsed since that. And then we have VR, which is a clock valuation for any R, which is the subset of C, and essentially is the clock valuation that agrees with my previous V, except that all the clocks that are included in R are going to be reset to 0. Once more, V of R is an updated, given V of R is a clock valuation that agrees with V on all the clocks except for those clocks that are going to be reset. The clocks that are going to be reset are going to take value 0. Okay, so the semantics of timed automata are defined in terms of transition systems. So we define for a timed automaton A an infinite state transition system, which includes states. So what is the difference between states and locations? So we know what locations are. State is a pair that has two components, the location and the clock valuation. Essentially, it collects all the information about all the clocks at any point in time, plus the current location of the automaton. And then we have the initial states. LV is an initial state if L is my initial location and all the clocks are initially mapped to 0. And then we have to define transitions. In transition systems, we have two kinds of transitions. Either we have time transitions or we have location switch transitions. So for any non-negative real number D, any state LV after D units of time is going to transition to a new state where the location is unchanged. However, the value of all the clocks have been increased by D. Location switch is instantaneous, means that what happens is that during the location switch, we have an action taking place on some input A. So the location is going to change from L to L prime, and V is going to change to V prime. And the only thing that would cause V prime to change is possible reset. Because as I said, the location switch transitions are instantaneous, means that they are not going to consume any time. However, due to resets, my clock valuations can be updated. And this is how it is updated by V prime. Okay, so now let us look at an example of states of some simple timed automaton. So I have a timed automaton here. Two locations are shown here, N and M. Observe that there are no clock invariants. And the transition on A takes place when the current value of clock X is less than or equal to 5 and Y is greater than 3. So the state at this point includes 3 pieces of information: my current location, which is N, and my value of clocks X and clock Y. So now, we said earlier that there are two kinds of transitions. One transition, the first transition, takes place on action A. As a result of that, we see that the location changes from N to M. The value of clock X before the transition was 2.4, but because during the transition, the clock gets reset, now the updated value of clock X is 0. However, the value of clock Y has not changed, as I said before, because the transitions, the switch, the action transition are instantaneous. They do not take any time. The second transition is different. It's a time transition, which means that while the automaton is in location N, it can just stay in location N. If there is no invariant, it can just stay there forever. So let's say that in location N, it waits for 1.1 units of time. So after that, the new state includes the same location N. However, the value of clock X and value of clock Y are both updated or increased by 1.1 units of time. Okay, so the next natural question is that if timed automata are extensions of finite state machines, what would be the language of timed automata? We know what would be the language of finite state machines. In general, if we have a set alphabet, which are my actions, and we can, so alphabet is sigma, then sigma star is going to give us all the possible words that can be generated using the members of the alphabet. And now the language is any subset of sigma star as long as the members of this L language satisfy some property. For example, L1 defined over the alphabet sigma could be the set of all words starting with an A, or L2 could be set of words with a non-zero even length. But if we want to extend this so that we define the languages for timed automata, we need to take into consideration the time actions also. So we define timed words. Timed words are essentially extensions of words with time. So I have my words as before, like W is A1, A2, AN, which is any member of sigma, sigma star. And then I have to also specify a time sequence. So A1 corresponds to tau 1, AN corresponds to tau n, which means tau 1 to tau n are interpreted as the time at which these actions have taken place. For example, if my alphabet is A and B, an example of a timed word would be AA 0.8, 2.5. What does it mean? It means that this automaton accepts a language that, a string AA, where the first A occurs at time 0.8 and the second A appears at time 2.5. Equivalently, we could represent this by a sequence of pairs like A, 0.8, A, 2.5. Both of them are used. I personally prefer the second one. So a set of timed words over the alphabet sigma that all satisfy the same time constraints essentially generates the language of an automaton. For example, here we have this timed automaton and the language is A followed by B followed by either A or B, 0 or more A or B, as long as the time difference between the first B and the first A is less than or equal to 2. So now observe that the first, on the left-hand side, I have A appearing at some time between 0 and 1, and the first B appearing at some time between 1 and 2. And after that, I have another B. So the language is A, B, B. But as you see, the time constraints, in particular, the time difference between B, the first B, and first A is less than or equal to 2. Therefore, this timed word is accepted by this machine. However, on the right side, I see another example of a timed word that cannot be accepted by this machine because the first A appears at some point between 0 and 1, whereas the first B appears after time 2. So the difference between these two events is more than 2 units of time. Therefore, ABB, the second ABB, does not satisfy the timing constraints specified by this automaton. Therefore, it is rejected. Okay, so we say, as we said, a time language is a set of timed words. And now for a timed automaton, the language of a timed automaton becomes a set of such timed words, which we will call it a regular timed language. So in other words, if I have a timed automaton, its language is called a regular timed language. Okay, so what is the relation between, there are several interesting questions that we want to consider. First of all, we studied timed automata because we want to specify the specifications of real-time systems, and immediate natural questions are, how about some interesting properties of the system, like safety properties or basic liveness properties that we are interested in verifying? What is the relation between all these and the language that a timed automaton accepts? So these are some fundamental questions that we would like to explore a little bit. So safety properties in general, intuitively, means that nothing bad will happen, where liveness properties specify that eventually something good will happen. When we say basic liveness properties, these are all those properties that are omega regular properties, means that these are properties that are going to be repeated infinitely often. And it turns out that both of these kind of properties, both safety and basic liveness properties, are introduced to emptiness problem. But what is emptiness problem? Given an automaton, the emptiness problem is asking the question whether the language accepted by a timed automaton is empty. So to answer this question, we must determine if some final state is reachable from an initial state in the state transition system corresponding to a timed automaton. So we are given a timed automaton, we have its corresponding state transition, and we would like to know if some final states are reachable when we start from the initial state. Therefore, verification problem, earlier we said verification, some verification problems are essentially reduced to emptiness. And now we are saying that emptiness can be solved by reachability. So that means that verification problem is essentially reduced to reachability. So reachability analysis is the process of computing the reachable states of a system. But what are the challenges? We earlier said that the state transition system corresponding to timed automaton is infinite. Let us consider a very, very simple case where we have only two locations, L0 and L1, and the guard on transition from L0 and L1 is x greater than or equal to 2. Such a very simple automaton give rise to an infinite state transition system. So you see from L0, when the initial value of clock x is 0, we have infinite number of transitions possible just because time can take infinite number of values. So the key questions that we face are, is it possible to somehow analyze this state transition system in a finite way? And the other fundamental question is that, is reachability problem decidable for timed automata? So in order to answer that question, the answer to both questions is yes, and it is possible using constructing a finite abstraction of the state transition system of a timed automata. So the idea is that infinitely many clock valuations can be categorized into finitely many equivalence classes. And this is done through a construction of a finite quotient. The idea will be that equivalent classes will all exhibit similar behaviors. So the construction uses an equivalence relation on the state space. Essentially, we say two states. Remember, what was the definition of a state? A state was a pair, including a location and a clock valuation. So we say two such states are equal if they agree on the integral parts of all clock values and on the ordering of the fractional parts of all clock values. So what is the definition? Let us assume that D is some real positive real value. Then we define the integral part of D to be the integer part of D, and the fractional part of D is defined by this function. For example, for any D, D can be written as a summation of its integral part and fractional part. If my D is 2.345, then the integral part is 2, obviously, and fractional part is 0.345. So we said that two states are equal if their locations are the same. Moreover, they agree on the integral parts of all the clock values and also on the ordering of the fractional parts of all clock values. For example, if in one state I have clock X that has value 2.5 and clock Y has value 3.7, you see that the fractional part of clock Y is larger than the fractional part of clock X. Now, in another state, if I have the value of clock X being, let's say, 10.1 and the value of clock Y is 10.9, again, the fractional part of clock Y is larger than fractional part of clock X. Therefore, these are actually that was not a good example because they would not agree on the integral part. So the integral part has to be equal, and then the ordering between the fractional parts must be preserved. So why do we need to, what is the significance of the integral parts and ordering of the fractional parts? The integral parts are needed in order to determine whether or not a particular clock constraint is met, while the ordering of the fractional parts is needed in order to decide which clock will change its integral part first. Okay, so now we are going to, for a timed automaton, and for a clock, for any arbitrary clock in a set of clock values, we determine the largest constant with which the clock is ever compared. It could be in the constraints of the guards, or it could be an invariant. So C sub x is the largest constant with which clock x is defined. Why is it important? Because when we want to create all those equivalence classes, this becomes important. So let us define what we said previously, and let us formalize it. So we say two clock valuations V and V prime are equivalent if and only if for every clock x, the valuation, the integral part of valuations of clock x, the integral part of valuation of clock x using V and V prime are the same. And moreover, if the fractional part of any clock x is 0, then the fractional part of clock x in valuation V prime also has to be 0. And the last bullet point is essentially what I said before, that the ordering between the fractional part must be preserved. So now we define the equivalence classes. So if V is a clock valuation, then we define the equivalence class represented by this clock valuation as the set of all clock valuations that are equivalent to V. And equivalence was the thing that we just defined in the previous slide. Once more, two valuations belong to the same, are equivalent if they essentially evaluate clocks in such a way that clocks agree on their integral part, and the ordering between the fractional part is preserved. Now, we give a name to such equivalent classes. So an equivalent class that is generated by some clock valuation is called a region. So here's an example. Let's say that I have two clocks x and y, and here I have a region, which is an equivalence class, which means what? Means that in this region, the value of clock x is between 0 and 1. The value of clock y is also between 0 and 1. And moreover, the value of clock x is less than 1, less than y always, which means that the ordering of the fractional part between x and y is such that the clock x always has a smaller value than clock y. Observe that by this kind of abstraction, we are going to have only a finite number of regions. So previously we had infinite number of states in our state transition systems, and the goal is to essentially create a finite abstraction of the system so that reasoning over the system becomes possible. Intuitively, two regions are equivalent, or two clock valuations are equivalent if and only if they satisfy the same set of clock constraints. So observe that, for example, here, this clock region that is specified when the value of clock x is 2 and the value of clock is 1, y is 1, there is only one valuation that can fall into this equivalent class. the reason is that we said two valuations can belong to the same region or to the same equivalence class if they agree on their integral parts of clocks and the ordering of the fractional parts are preserved. But if the value of clock X is precisely 2 and the value of clock Y is precisely 1, then there is no other valuation that can be equal to this valuation. Therefore, this particular equivalence class or this particular region has only one valuation inside that. Another example is this straight line here, when the value of clock X is between 2 and 3, and the value of clock Y is exactly 2. Okay, so now let us see what happens. The idea is that we want to essentially transform the state transition system of a timed automaton, which has infinite number of states, to something finite. And the idea is that, okay, we should be able to handle all the time operations, in particular, what happens when clocks are reset. So let us consider this region R, which is one equivalence class or a region. When we reset the clock X, now my region is going to be updated to this straight line between 0 and 1, which means what? Because clock X has reset, now I have this straight line where the value of clock Y is between 0 and 1, and X has value 0. Similarly, in that region R, if clock Y is reset, then I will get this straight line on X axis where the value of clock X is between 0 and 1 and value of clock Y is 1. So now let's say enough time elapses so that both X and Y, initially X and Y are between 0 and 1, and let's say enough time has elapsed so that the value of X is between 1 and 2, and the value of Y is between 1 and 2 also. So we end up at this yellow region, which is a successor, time successor of region R. So depending on how much time has elapsed from this region R, there are various possibilities. We could go to this region, we could reset the clock, go to this region, or we could go to the yellow region, and so on. So now, I think this is what I said previously, but the important thing is that now we are going to establish time abstract by simulation. If two states are equivalent, then a discrete switch from one can be matched by a corresponding discrete switch from the other, leading to an equivalent target state. So what are these discrete switches? These are the actions, remember earlier we said there are two kinds of actions. Either we have discrete switch actions or we have time actions. So now, if two states are equivalent, which means if two states belong to the same region of the automaton, then a discrete switch from one can be matched by a corresponding discrete switch from the other, which means that they after the transition, they are going to end up in equivalent target states. Means that if they begin with equivalent states, after the transition, they are going to end up in the same equivalent state. And what happens to time actions? If the automaton can wait for delta units of time in one state, then it can wait for delta prime units of time, which results in equivalent state. So this means that we have established the region equivalence, which is a time abstract by simulation. So what is time abstract by simulation? We say if two valuation, clock valuation, V and W are equivalent, and from location L with time valuation, clock valuation W, it is possible to take action A to go to location L prime with clock valuation W prime for some W prime, then there must exist some clock valuation V prime which is going to be equivalent to W prime, such that from location L with clock valuation V, I can take the same action A, go to L prime, V prime. That was action transitions. So essentially, intuitively, it means that if two clock valuations are equivalent, then if one of them can take an action transition or a discrete switch transition, then the other one can also take that discrete switch transition, and they are going to end up in two states that are going to remain equivalent. How about delay transitions? That means that if two clock valuations are equivalent, then for all real numbers, then there must exist some D prime such that W plus D is equivalent to V plus D prime. What is W? W is my initial clock valuation. After D units of time, it is going to be equivalent to V plus D prime. Means that we do not need to concern ourselves with the exact delays, D and D prime. They don't have to be exactly the same. The idea is that as long as there exists some D prime such that from both these clock valuations, we can essentially make some time transitions so that the resulting clock valuations are still equivalent, then we say that this satisfies the requirements of time abstract bisimulation. So for a timed automaton A, we define the quotient of S of A. What was S of A? S of A was the state transition system of A. The quotient of S of A with respect to region equivalence is called the region graph of A. And the idea is that, as we said before, if V is some clock valuation, we already established the equivalence class that is represented by this clock valuation, which is the set of all clock valuations that are equivalent to V. Then we are going to now essentially transform our state transition system to a new system, which is called a region graph. How? Our previous state, remember, we had infinite number of states. We had states L, V. L was a location, V was a clock valuation. Now we are going to essentially move to symbolic states where my states are going to be pairs. The first item of the pair is a location, and the second item is the equivalence class represented by that clock valuation, which means the set of all clock valuations that are equivalent to V. Now, region graph of a timed automaton is an unlabeled transition system where states are symbolic states and transitions are defined as follows. So if in my initial transition system, I had a transition from LV to L prime V prime on some action A, then on the corresponding graph, region graph, I'm going to have a transition from L and equivalence class of V to L prime and equivalence class of V prime. Similarly, if in my initial state transition system, I could take a time transition of unit D, then that means that I can still take a transition from L and equivalence class of V to L and V prime, which is the equivalence class of V prime. Observe that now in these transitions, no longer we have any labels, because the idea is that the time constraints are already captured in my regions, because every region is going to capture all those clock valuations that satisfy some time constraints. So I no longer have to concern myself with time delays. So that's why if you observe here on my transitions, these are called unlabeled transitions because they are no longer needed. So now it turns out that reachability for timed automata now can be carried rather than on the state transition system on the region graph. So because the region graph is finite, there are only finite number of regions, suddenly reachability becomes decidable. So the idea is that we want to know if, what is the meaning of reachability? Beginning from some initial state, we would like to know if some particular state is reachable in the timed automata. That will be translated to answering the question whether in the in the corresponding region graph, it is possible to go from the initial region to some region such that my final clock valuation is a valuation inside this equivalent class corresponding to it. So the consequence of this is that the region graph for A can be used to solve language emptiness for A and answer reachability queries for A. So the idea is that those questions that previously were not, we would not be able to answer using the transition system now become feasible by using the region graph. So emptiness and reachability can be solved in time that is linear in the number of vertices and edges of the region graph, which is linear in the number of locations and edges of A. It is exponential in the number of clocks and exponential in the encoding of constants. And here's an example. Let's say that I have this one location L, and there is a transition where that can take place when the value of X is greater than or equal to 2. While this transition is taking place, clock X is reset. So here in rectangles, I see these are my regions, or these are my equivalence classes generated by clock valuations. So location L, initially clock X is 0. Now, it is possible to go from this region to another region where the value of clock X is between 0 and 1. From here, it is possible to go to yet another region where the value of clock X is exactly 1. And from here, it is possible to go to another region when the value of clock X is between 1 and 2. Why is it that these has to be separate regions? Because of the things we discussed before. We said that two regions, essentially two clock valuations, will be equivalent if they agree on the integral parts of the clocks. So you see that going from B to C, the integral part of clock X has changed, right? So that is why it becomes a new region. And from D, you can continue and see that as time elapses, we will be able to essentially move to various regions of the region graph. And finally, here, as I said before, because there is no invariant in this location L, the region F, we have X greater than 2. So the reason that this region is reachable is because there is no invariant that force this timed automaton from progress. So it is possible for this automaton to stay in location L while the value of clock X is greater than 2. Okay, what have we achieved by this? So from timed automaton, we established its region automaton, which is large but finite. And it turns out that it is exponential in the number of clocks and in the constants, but it can be used to check for both reachability and safety properties, and also for liveness properties. So now we want to talk a little bit about what is the relation between all these and the language of a timed automaton. We previously talked about the time language, and we said a time language is timed regular if it is accepted by some timed automaton. It turns out that timed regular languages are closed under union and intersection. But how about complementation? But why is it that complementation is so important? So here's an example of a timed automaton that that accepts a language where the language is sequences of A's and B's such that there is A at some time T and no event at time T plus 1. And the complement of this language is not timed regular. So that means that timed regular languages are not closed on their complement. But why is it that complementation is so important? The reason complementation is so important is because in general, we are interested in inclusion problem, which means given two timed automata A and B, we want to know if the language of A is a subset of language B. This is interesting because from the perspective of formal methods community, what happens is that we have the system, let's say specified as some timed automaton B, and the specification is specified as some timed automaton A. And in order to verify the correctness of the system, we want to make sure that the language of B is included in language of A. Means language inclusion is fundamental for model checking. But this is equivalent to checking whether the language of B intersects with the complement of language of A is empty. And it turns out that this emptiness, the complement can be checked only when the timed automaton is deterministic. So therefore, inclusion and equivalence problems in general are undecidable for timed automata. If the timed automata is deterministic, then we can compute its complement, and therefore we can answer inclusion problem. But in general, both of these problems are undecidable. So let us look at a very few subclasses of timed automata where inclusion problem can be answered. The first example is deterministic timed automata. The idea is that, so far we have not made any distinction between deterministic and non-deterministic timed automata, but now deterministic timed automata, we have, if we have the same action, if we have several transitions out of one location, which are all labeled with the same action, then we want the guides to be such that two guards at the same time cannot be satisfied. Plus, we want to have only one single initial state, and moreover, we do not want to have any transitions on epsilon. Such an automaton is called deterministic timed automaton. A deterministic timed automaton has a unique run on every timed word, and it is closed under not only union and intersection, but also on complementation. It is strictly less expressive than general timed automata, which means that the set of languages accepted by the class of deterministic timed automata is a subset of the class of all timed languages. Given a timed automata, checking whether it can be actually determinized is undecided. So far we identified one useful class, deterministic timed automata, that can be complemented. Because they can be complemented means that inclusion can be solved for them. Therefore, they are interesting from the model checking perspective. Another class of timed automata are event recording automata. So the idea is that for every event A, there is a clock X sub A that records the time of the last occurrence of A. For example, here I have the first A and followed by B. And when I say XA less than 1, that means that the time that elapsed from the last occurrence of A must be less than 1. And then I want the X sub B to be greater than 2 when D occurs, which means from the last occurrence of B, I want more than 2 units of time to be elapsed. So event recording automata can be easily determinized. The cost that is paid is exponential growth in the number of locations. But the thing is, we obtain some determinizable automata, and therefore we can complement them. Event clock automata are extensions of event recording timed automata with prophecy clocks. What are these clocks? These clocks essentially predict the future. For every event A, there is a clock Y sub A whose value at any point is the time that must elapse before the next occurrence of A. For example, if we consider the timed word that I have shown here, then when reading the third event, the value of X sub A is 0.3 because there is a difference of 0.3 units of time between the first A and the third action. And also the value of Y sub A is 0.25, which means that from the third action until the last occurrence of A, which is the last action, we have exactly 0.25 units of time. Prophecy clocks add to the expressiveness of event recording automata. So now it turns out that the value of any clock at any time only depends on the timed word that is being processed, not the run of the automata, which means essentially that the consequence of that would be event clock automata can be complemented, which means these are closed under complementation. So that was the second class of useful timed automata. And finally, one approach to get a more tractable subclass of timed automata is to restrict the resources of a timed automata that we are going to use. For example, checking language inclusion between two timed automata A and B is decidable when B does not have any epsilon label transitions, and moreover, either B has only one clock or the only constant that appears in the guards of B is 0. So you see, in general, we are saying that language inclusion problem for timed automata is undecidable. And we are trying to hunt for some classes that would make that problem decidable. And there are some other, not classes, but there are ways to essentially control the resources of a timed automata. What are the resources of timed automata? The most important resources are the clocks of a timed automata and the maximum constant that appear in the guards or invariants of timed automata. And this slide shows that the language inclusion can be solved if we do not allow epsilon transition in automaton B, and moreover, if automaton B has only one clock and the only constant that appears in the guards of B is 0. And that was it. If there are any questions.
Thank you, Neda. That was very interesting. Timed automata are very complex structures. So I think you've explained it. It hopefully made it easier for people to understand it. We have time for some questions. I have one question. Timed automata are very expressive, but at the same time, they are very difficult to analyze because of the expressiveness. And as you mentioned, there are restrictions that make it more amenable to analyzing it. So my question for you is it practical to verify timed automata? Is it practical to actually construct these region graphs, or are they still too complex to analyze in practice?
Actually, that's a very good question. So unfortunately, I didn't have time to talk about zones, because what we have here, we talked about clock regions that essentially enable us to do any kind of reasoning. I mean, at all about timed automata, because if we are dealing with state transition systems, the state space is infinite, we cannot do anything. But by constructing clock regions, we can at least do something, reason about like emptiness and reachability. However, what happens in practice is that because the number of clock regions is too much, finite, but it's still too much, clock regions are not used in implementation. What is used is clock zones. So essentially, several clock regions can be collapsed into only one clock zone. And now we are going to have a significant reduction in the number of zones that we are going to have. In fact, there are tools like UPAL that is the main tool for implementing timed automata. And that tool does not use clock regions or region graph, but it works with zones. So the idea is very similar to clock regions, but rather than working with clock valuations, we are directly working with clock constraints. Essentially, each zone becomes clock constraint. And then several clock valuations are going to be collapsed into one clock zone, and we are dealing with more tractable, essentially graph, and easier to evaluate, but still challenge.
Yeah, well, I can attest for the practical aspect of RuPaul. I have a few students that work with it. So this is actually quite interesting because when I was doing my PhD, I argued constantly of the not need for complex rich models such as timed automata because the domain I was working with didn't require them. And that's the message that I left at the time. And then eventually I started working with different domains in which the richness of the timed automata and the clock zones are so important. So my take on it, and I would like your opinion on it, is that when you have an artificial domain, such as several types of software or hardware in which you construct things, and this construction, it has to take into account some finiteness. Otherwise, we are not able to construct these things.
Exactly.
I mean, we have to be able to measure them in some way. And for many of the applications, not for those systems, not all of them, you can get away without a timed automaton. But I started working with biological systems and modeling biological systems. You can't do with timed automata because there is no inherent construction. When you construct something, you have to simplify it so that you can build it. But for a biological system, you're not constructing it, you're just observing what nature does. And then it's way more complex. And that there is no hope of doing it without timed automata, without time-dense systems. And that's why we're using UPAL. It has been working fine with the limitations that we understand. I mean, it explodes as all verification tools do, but it works well. So my summary of this observation is, for many of the artificial things we build, sometimes we can get away without timed automata. But for applications such as those that come in nature, it's very difficult to do so because of the complexity of the domain. What do you think of this, Neda?
Well, right? I think it also has something to do with the properties that we would like to verify. If the properties that we are trying to verify are untimed properties, simple reachability properties, for example, even though the system might exhibit some time aspects, means it is a timed model, but we don't really care the properties that we are going to verify has nothing to do with time. Then there is no reason to do timed automata. But if we are dealing with verifying time-related properties, then we got to use some tool that will enable us to model time. Timed automata is one of them. Of course, there are various other models. I would say as long as there are good supports for the models, good tools that support the models, why not? UPAL is a good tool that provides very good support for timed automata. The challenge is get the models correctly. Once we get the models correctly, then UPAL does a good job at doing that. But what you said, I agree with that, but I think that the properties to be verified must also be taken into consideration in what is the model that we are going to choose.
Yes, absolutely. You're right. Yes, that's very interesting. Thank you. Any more questions? Okay, I don't see any more questions. So let's thank Neda for the very interesting talk. And I guess we'll end the session and we should start again in about half an hour, if I'm correct. Tiago, are you there?
Yes, yes. Thank you, Neda. I think with this This introduction will clarify a lot of the next presentations, the next technical session, which will start at 3:30 here at this same room. So we have a 30-minute break before getting there.
Okay.
Thank you. I just want to maybe announce to the authors of the next session. So is to be present at least, I don't know, at least 5 minutes before, and to introduce yourself to the session chair, which will be, who's the session chair is Thierry.
Myself.
Hello, Thierry.
Hi.
Hey, great.
I'm on the tunnel, as usual.
Yeah, yeah, it's kind of dangerous, isn't it?
Yeah.
Okay, I'll see you in half an hour.
Okay.
Goodbye.